Namaskar my dear friends. Let us try to understand micro module switching regulators. So in this kind of switching regulators, what are the different parameters or different features that is involved, and why do we go ahead with micro modules? Okay, so micro modules means basically in all switching regulators you will be required to select an inductor. Okay, so generally in micro modules these inductors are inbuilt inside. Okay, so you don't have to put external inductors in your circuit design, and that's how it saves you a lot of time, and it saves you from selecting a magnetic components. We'll try to understand this micro module switching regulator design with one of the example, and that example will take up LTM8051. This is going to be very good IC as well. It can give you a real-time application for your industrial supplies, or it can be used in medical equipments, as well as it can be used in automation equipments and some measurement equipments like oscilloscopes and all. Okay, and this particular buck regulator is going to take up to 40 volt input, and it can give you output of 1.1 amperes. Okay, it can be even higher. And the best thing of this particular micro module switching regulator is it has 4 outputs. Okay, so our main purpose would be to understand what is micro module and how it is going to serve you in a better way, like how it can like make your design much easier, much compact and easy to implement in your applications. Okay, so let us proceed. As you can see, I have told you the part number is LTM8051, and this is the link for product details, and this is the link for datasheet of this particular LTM8051 micro module switching regulator. As you can see, it is having quad 40 volt input with silent switcher micro module regulator with configurable 1.2 output 1.2 ampere output array. Okay, so if you see the features, as you can see here, it has 4 complete step down switching power supplies, then it has low noise silent switcher architecture. The best part is it is compliant of class B for CISPR 22. So CISPR 22 class B compliant, CISPR 25 class 5 compliant. Then it can take wide input range from 3 volt to 40 volt, and it can give you the output voltage range from 0.8 volt as low as 0.8 volt, okay, to up to 8 volt. The thing is, it can give you 1.2 ampere continuous current output per channel at 12 volt input, okay, and 3.3 volt output if you want to have at 25 degrees 85 degrees centigrade. It can give you even higher current, let us say 1.5 ampere continuous current per channel at 60 degrees centigrade. So see, the temperature has reduced, then it can give you the higher current as well. Okay, it has multi-phase or multi-micro module paralleled for increased output current. So what happens is, as you can see from this guy, each of the output channel can be configured with different voltage output, voltage out 1, voltage out 2, voltage out 3, voltage out 4. Okay, the thing is, the beauty is, if you want you can parallel them both. Okay, so parallel them both, then it can give you 2.4 ampere put together. Okay, so 1 and 4 can be paralleled, and you can get a higher current. Similar to that, last two can be paralleled and you can get higher current, and at last you can parallel all of them to get the highest current, which is going to be 4.8 ampere. Okay, and it has 4 different switching regulator in a single package. That's the biggest advantage. Let's see more of the features and more of the applications about this particular LTM8051. Okay, this is a part number. Coming back to applications, so as I already told you, it has automotive test equipment applications. Then it can be used in your distributed supply regulations like DCS. Okay, or it can be used in a SCADA also. Then it can be used in industrial supplies or automations, and it can be used in medical equipments. Basically, like medical imaging requires very compact like regulators. It can be used in your wireless communications and oscilloscopes, like measurement equipments. So why they are used is this is the micro module that I am talking about, and this can be used in your transceiver power supplies or DAC power supplies or RF applications or ASIC power supplies and all. And this has been taken from Analog Devices video, where they have explained like what are the different applications, and we have also utilized in one of our automated test equipment this particular application. Okay. Now coming back to typical application schematic. So application schematic, if you see, you can see like we have 1.8 volt output to 5 volt output set from 7 volt input to 40 volt input. Okay, and we have quad step down converter. So let us say we are going to give input here 12 volt. Generally 12 volt input is a standard input supplies that is there. What they have done is V input 1 and run 1 4, as well as V input 4 and V input 2 3. 2 3 is together. Okay. So they have been supplied with the input voltage with a capacitor. So capacitor will be required respectively. I will tell you later on in our design. Like each of the input has to have a separate input capacitors. So generally like in dataset it is given 1 microfarad, but I will suggest you to put 10 microfarad plus 0.1 microfarad in each one of them or more. Okay, based on the ripple removal or transient removal that you wish to have. Okay. Coming back to output settings, so there is no need of like a feedback resistors voltage divider like a design. It is just needing only one resistor to set the output voltage, as well as there is no need of inductor selection. Inductor is inbuilt inside. Okay, for each one of the outputs. So this is how you are going to get a very simple design with very compact design, and you have a resistor setting for the switching frequency application. So you can set your switching frequency, let us say from I think 0.3 megahertz, that is 300 kilohertz to 3 megahertz. We will have to check exactly what is the frequency range. Okay. As you see, the efficiency that is in like being achieved is more than 85%, or it is reaching up to 90% as well. So this is how it is more convenient. So before getting into the design, what we'll try to understand is what are the maximum voltage rating or maximum ratings for each of the pins, so that we do not like damage the ICs. Okay. So the input voltage run N, or like a power good N, can take up to 42 volt input maximum. So you have to make sure that these three pins do not get more than 42 volt, otherwise the IC will be damaged. N means like let's say V in 1, V in 2, V in 3, like that it is run 1, run 2, run 3, PG1, PG2, like that it is there. Similar to that, V output and bias voltage cannot be more than 10 volt. However, it has been restricted to 8 volt output only. So you have to make sure you do not design your output voltage more than 8 volt. Okay. So I will suggest you to go ahead with 7.5 volt V output maximum setting. Generally, this particular IC is being used for 1.2 volt output, 1.8 volt output, 2.5 volt output, 3.3 volt output, and 5 volt output. Okay, so these are the 5 outputs that I have been always using in our like applications. We have feedback pin and like track, soft start pin, share pin, RT pin, and VCC pin. So they can take up to maximum 4 volts. So generally it will be very less, and there you don't have to worry about, like it will be always lesser. We have sync pin which cannot take more than 6 volt, and it has like temperature, internal temperature up to 125 degree centigrade. Okay. Coming back to the pin configuration. So this is a BGA package with 91 pin configuration. Okay. So as you can see, this has been like organized in bank wise. So let us say bank 1 with V output 1, then bank 2 with V output 2, then bank 3 V output 3, and similar to that bank out V output 4, bank 4 V output 4. Okay. The middle one, as you can see, the dark area, which is it is actually bank 6, which is going to be a ground. Okay. We have V input 1, V input 4, and then we have sync 2 3, sync 1 4. 1 4 means channel 1, channel 4. 2 3 means channel 2, channel 3. Okay, we have clock output 2 3, clock output 1 4, run 1 4 and 1 2 3, and this is feedback 2, feedback 3. So this has been done very easily. FB2 is almost close to V out 2 and FB3 is close to V out 3. Similar to that, FB4 is close to V out 4, it will be here, and FB1 is V out 1. Okay, so this is how it is mentioned. Okay, it is very easy to recognize the pin configuration of this particular IC. They have given a list of table as well, how the pins are arranged. So as you can see, the pins were arranged from like 1 to 7 and then A to let's say N. Okay, so this is the let's say if I want to have A1, then this will be the pin A1. If you want to have D3, then the pin number D3 will be D is this and 3 is this, so pin number D3 is this. Okay, so this is how it is recognized. So if you are a beginner in BGA package, how to understand the pin number, then pin number is actually understood by rows and columns, and accordingly this is the rows and this is the column, accordingly you can understand. So let's say H3, so H3 will be no pin is there available, that you have to understand, or H7, so H7 will be this pin. Okay, so you can have this particular list of config pins, so that you can design your own symbol for this particular IC. Coming back to pin configuration, so as I already told you, like it was very straightforward. V output means, V input means like ground pins, then clock out pins and run pins. So this is already there in our data sheet, so we'll be explaining while designing the circuit. Okay, coming back to ordering information, so ordering information, it has like three parts. One is LTM8051 EY, then another one is IY, and another one is without lead finish. Okay, so has PBF is with lead finish, and has without this is without no lead finish. Okay, so our utilized part was first part, which is LTM8051 EY has PBF. Coming back to block diagram, so block diagram, as you can see, we have V input 1 pin, V input 4 pin, and V input 2 and 3 pin. Okay, so input 1 means for channel 1, input 4 means for channel 4, and input 2 3 means channel 2 3. Got it? Similar to that, we have channel 1 and 4 are actually parallel, so run 1 4 is together. Similar to that, run 2 3 is also together. And we have 4 channels, so we have 4 track soft start pins. So tracking soft start pin is tracking 1, tracking 4, and tracking 2 and tracking 3. Why do we understand the block diagram? Is actually gives you the understanding like how it is working inside. So let us say V input 1 is coming here and it is reaching to this high MOSFET, low MOSFET. This is my high MOSFET, this is my low MOSFET. Okay, low side switching and high side switching. And this is the inductor that was supposed to be designed at outside, and this is the feedback resistor that we generally design. As you can see, like this will be generally feedback without micro module devices, so this will be considered as R1 and outside it will be R2, like that we will be seeing. Okay, so this is very simple to view. You can see inductor R1 R2, which will be have to be designed outside. Generally in all the switching regulator that we have already seen, there we had required to be designed the value of inductor and the complete value of feedback resistor voltage dividers to set the output voltage. The beauty of this particular design is it has internal filter capacitor like 10 microfarad, 10 picofarad and 3.3 nanofarad, so that the output bulk capacitor only will be required to set your output voltage. Okay, same thing is there for all the 4 channels, and we have here control signals that is there down, so we don't have to worry about them. Coming back to some of the testing that is done by the particular demo board that is already there by Analog Devices itself. So as you can see, they have tested it for CISPA 22 class B emission test, and you can see the input was 12 volt and output was 1.2 ampere per channel, with V output 1, 2, 3, 4 as 5 volt, 3.3 volt, 2.5 volt and 1.8 volt. And with class B CISPA 22, rating, this is the like a limitation that is there, like 40 dB, and it is going up to like a 47 dB here. From frequency that is taken is around, I think, 10 megahertz to 1000 megahertz. Okay, so it is well below the limit, right, upper limit. Similar to that, they have tested it for CISPA 25 radiated emission with class 5 peak limit. Okay, so their demo board actually meets the requirement of the limits of CISPA 22 and CISPA 25. Okay, coming back to design and details, like we are going to now move into the main design phase, like how we can design our uh, switching regulator with all these informations for our application. So first of all, we have to set the output voltage. Okay, so you can use this formula like RFB is equal to 249 divided by V out by 0.8 minus 1 to set your output voltage. So as you can see, we had already inductor and one resistor is already there. The only thing is we have to design this particular resistor, which is RFB. Okay, and this RFB, the calculation will be like this: 249 divided by V out. So suppose I want to set it 5 volt, so what will happen? 249 divided by 5 divided by 0.8 minus 1, so this is going to be 249 divided by this is going to be 6.25 minus 1, that is 5.25. So this much kilo ohm, so that is going to give you 47.4 kilo ohm or something. So 47.5 kilo ohm will be the best choice for your output setting to 5 volt. Similar to that, if you want to set the output voltage to 3.3 volt, then 39.2 kilo ohm will be the calculation for feedback resistor, and for 1.8 volt it will be coming up 200 kilo ohm. Going to set for 1.2 volt output, we can have RFB as 498 kilo ohm. Okay, so all these calculations, if you want, you can do by yourself, or otherwise you can look into the table 1 to get your like desired input range and what is the output voltage setting and their corresponding input capacitors, output capacitor, RFB values, that is feedback resistor value, and the switching frequency setting resistor value. Okay, the bias voltage that will be connected as indicated, that we will look into that. Now let us see table 1 to understand what are the different informations that is given here. So as you see table 1, the recommended value that is given for different input values. So suppose you have to set a value of 1.2 volt or 1.8 volt or 2.5 volt, 3.3 volt or 5 volt. Okay, so these are the 5 readings generally I always recommend to go ahead. So let us say input voltage I am setting to 12 volt, and then you can put a resistors of 499 kilo ohm, and you have to have a input of 1 microfarad 50 volt settings with output capacitor of 2 times 100 microfarad, and you can put the bias voltage from like 3.2 volt to 10 volts. Generally I keep a 3.3 volt bias voltage, and feed forward capacitor will be put at 22 picofarad. If you want to have 650 kilohertz like a switching frequency, then you can put the RT value resistor of 49 kilo ohm, 49.9 kilo ohm, and this is how you are going to set up. But I'll suggest you don't go ahead this much complex. Just set the RT value to somewhat like, let's say, 700 kilohertz or 1.2 megahertz or 1.6 megahertz. These are some of the like good choices for all my designs for different applications that I have been using earlier. Okay, so this is how you can utilize this table. However, in my application we will be showing you what are the different values of C input and C output. Generally I prefer to have extra input capacitor as well as extra output capacitor, which is recommended by the data sheet. We will be adding more than this. Okay. Coming back to switching frequency setting, so switching frequency setting, as I told you several times, that there is a RT resistor that will help you to set the switching frequency of your like micro module switching regulator. So this can be set from 300 kilohertz to 3 megahertz, and as you see that lower the switching frequency, you may need to have higher inductor, which is already inbuilt here, so there is no choice, there is no problem there. But I'll suggest you to go ahead with a nominal switching frequency, which is going to be 700 kilohertz or 1000 kilohertz or 1600 kilohertz or 1.6 megahertz. Coming back to some of the other parameters, let's say bias pin configuration. So bias pin consideration, you have to understand, like this basically provides the power for internal switching applications or something like that. So this can be operate other internal circuitry also. If the output voltage is programmed to 3.2 volt or higher, then bias pin you can directly connect to your V output pin. So let us say you are going to design your V output to 3.3, so connect your bias pin to 3.3 volt. And if it is not that kind of output, like let's say it is lesser than that, then you have to have a separate input source for your bias pin. That's how, like if your V output pin is less than 3.2 volt, then bias can be tied to your V input as well. But you have to make sure that V input must be less than 10 volt. That's the understanding. Okay, so in all cases, ensure the maximum voltage that you are connecting to your bias N pin must be less than 10 volt. Coming back to load sharing, so load sharing, what I mean is, let us say you have to have a requirement of 2.4 ampere rating, okay, like 1.2 ampere it is going to give you per channel, so two channels you can put together. So this is how you will be load sharing. Okay, so channel, let's say 1 and channel 4 you can load share, and then channel 2 and 3 also you can load share. So in that case, your RFB will be designed in this manner, because RFB will be 199.2 divided by n times V output minus 0.8. So where n is actually the number of channels that you are going to put. Okay, so n will be 2 or n will be 4 if you are going to sort all the 4 channels. Good. So we have moved into that. Then this is the complete design of this particular IC. Now we'll try to understand the PCB design guideline that is given in the datasheet itself. So as you can see, you have to understand the placement of your feedback resistors and RT resistor, that is switching frequency setting resistor, must be very close to the possible respective pin. Okay, so you have to put the RT resistor as well as FB resistors close to their respective pins. You have to place your input capacitor as close as possible, and you have to connect them to the ground. Okay, then your output capacitor must be also as close as possible and connect them to ground. So input capacitor as well as output capacitor must be very close to the respective input and output of the particular channels. Okay, as you can see here also, they have like bank 2 was there, so C output 2 and C output 3 and C output 1 and C output 4. So they are very close to the respective pins. These 4 pins are V output 4, so they are very close to that. Okay, coming back to place C input and C output capacitors such that their ground current flows directly adjacent to the underneath. Okay, so you have to rotate them in such a manner that the ground actually directly goes into the internal circuitry of this is the ground share. Okay, so you have to understand that ground must be directly connected here. Okay. All right, so this was all about the PCB design guideline and the complete design circuitry of this. Now we'll try to understand three typical application that is given in the data sheet, and after that we'll try to give you the exact design that we have put in our design, so that it will help you for a real-time application. So as you can see, the first application in the data sheet, it is given as 7 volt to 40 volt. So let us say we are going to give 12 volt input or 15 volt input, or even 24 volt input also. If you want, you can give it. Okay, coming back to output settings, so 5 volt, 1.8 volt and 3.3 volt. 3.3 volt has been set to both the channels, channel 2 and channel 3. So there it is kind of a load sharing. Okay, so that's the reason the output current rating will increase here. Okay, Coming back to feedback resistor setting, so based on the calculation, feedback resistor setting for 5 volt is going to be 47.5 kilo ohm. For 1.8 volt, you are going to calculate the FB resistor, that is feedback resistor, to be 200 kilo ohm. Coming back to this channel, which is going to be 3.3 volt output, this FB resistor will not be calculated straightforward. You have to utilize the parallel channel method, and in that you are going to calculate this to 39.2 kilo ohm. Okay. Coming back to frequency setting, so FSW setting must be like there. So they have set it to 1.2 megahertz, which is going to give you a RT value of 24.9 kilo ohms. Okay. And if you want, you can set the switching frequency for different channels to different values. So I'll suggest you to keep both of them to like a single frequency. It will be easier for design. Otherwise you can go ahead with setting different switching frequency for different pairs of channels. Okay. So here also, if you want, you can put 1.2 megahertz, and so that you can make it 24.9 kilo ohm. Okay. Now coming back to input capacitors of respective inputs, V input 1, 2, 3, 4, everything, they have suggested you to keep 1 microfarad with like a 50 volt rating. Okay. I'll add you here, like put 10 microfarad in each one of them respectively, plus 0.1 microfarad also with 50 volt rating each one of them. 10 microfarad you can keep for 12 volt like rating, you can keep up to 25 volt rating, no problem. If you have an input of 12 volt, then you can keep it 25 volt rating. So this is the complete design that is there. Coming back to the output capacitor, so C output capacitor is here. So in the C output capacitor, if you want, you can keep it 47 microfarad plus one more 47 microfarad you keep, and plus 47 microfarad you keep, plus 0.1 microfarad like a filter capacitor you keep. Okay, so I'll suggest you to keep like this. Similar to that, you can have here 100 microfarad additional, 100 microfarad additional, and 100 microfarad additional, with each one of them having 0.1 microfarad parallel capacitors together. So this is how you are going to design the complete like a application circuit for your particular application. So alright guys, hope you have a good understanding now about this typical application and what are the different changes that you need to do to suit your real-time application for your particular design. Let us move to the other typical application. What they have done is they have a parallel input parallel to 3.3 volt at 5 amperes. Okay, so all the channels have been parallel, like channel 1, channel 4, channel 3, channel 2, channel 3. Okay, so all of them are going to give you 3.3 volt with 5 ampere rating almost, or 4.8 amperes rating. Okay, and as you can see, the switching frequency has been set to this particular value. I am not going to explain again and again. Here let's say we are going to give 12 volt. Similar to that, you have to keep the like input capacitors as I mentioned in the previous example just now. And here you can see there are total 400 microfarad capacitors plus 0.1 microfarad, and like additional, if you want, you can increase to 330 microfarad additional. Okay, so let us say one more 330 microfarad. Only one capacitor should be enough to put to have a proper power bank. Okay, coming back to the other typically like example. So typical example, what they say is one of the output 5 volt has been used as input to the channel 4. Okay, and this channel 4 is going to give you an output of 1.8 volt. So this is how also you can do. You don't have to always give input from external source. The output higher voltage like output can be used as a input for the lower voltage converters. That's the advantage of this particular IC. And the other two channel has been used as parallel combination to give you an output of 3.3 volt. Okay, and you can set the same switching frequency. Here it is set to 1.3 megahertz. So instead of that, you can always keep it 1.2 megahertz for both of them by putting 24.9 kilo ohm here and here as well. Okay, both of the places. Good. So this is the particular package information that you will see. This is the micro module that looks like from top, and the bottom is having like these are the balls that has been set, and you can have the understanding of this is just 11.25 mm cross 6.5 mm 6.25 mm, and the thickness is just 2.22 mm. So hope you have an understanding of now what is micro module and what is the advantage, like how you can make use of this particular design for different applications like medical imaging, wireless applications, or oscilloscopes, or measuring other measuring equipments, or designing the power supply for your DAC or RF or transceivers or different applications. And there is no need to select your inductors and separate like complex combinations of resistor configurations or like feedback resistor design. So all these things are made very easy in this micro module IC. Okay, so if you have a requirement of like a particular application circuit design for your any specific applications, you can always put down your queries in the comment box, and we shall be able to come up with proper answers or exact answers. Thank you so much.